My name is Snigtha Mohanraj. I am in the 9th grade at the Engineering and Science University Magnet School in West Haven. So your water may look clean, but it's actually contaminated with many pieces of microplastic. My project is called Ferrosponge, an investigation into the usage of metal oxides for microplastic and oil removal from water. So to give a brief overview of what I specifically researched in this project, I researched using metal oxides with an electromagnetic filter in order to remove microplastics from water. Specifically, I then investigated iron oxide nanoparticles that were applied to a sponge to be more easily implementable, and I tested other additives with the iron oxide nanoparticles in order to increase the effectiveness even further. In the end, I designed the final Ferrosponge prototype by coating a polyurethane sponge in a mixture that consisted of iron oxide nanoparticles and bentonite to effectively remove both microplastics and oil from water. So the overall purpose of this project, in a broad sense, was to determine an optimal method of removing dissolved microplastics and oil from contaminated water. But I wanted to make sure I did this in an efficient, cost-effective, environmentally friendly, and easily implementable way. Specifically, I then researched the usage of metal oxides for contaminant removal, and in the end, I researched different designs of the Ferrosponge, which was my effective implementation of metal oxides using a polyurethane sponge to remove microplastics and oil from water. So now I'd like to give a brief introduction into what microplastics are and why it's really important that we focus on removing them from our water. So microplastics are small pieces of plastic that are less than 5 millimeters in size. They pose both environmental and health hazards, as they can be toxic themselves or carry and transport toxins. 83% of tap water is polluted with microplastics, and 93% of bottled water contains microplastics. They are found nearly everywhere, but current water filtration processes are unable to remove these microplastics due to their extremely small size. Oil is another example of a prominent water contaminant, as many sources of water are contaminated by oils, which is usually crude oil since it's the most commonly used form industrially. Oil can enter our water through a variety of different ways, but the most influential manner that oil gets into our water is through mass oil spills. Increased intake of this toxic oil can lead to significant negative health effects, ranging from respiratory damage to a weakened immunity system to even an increased risk of cancer. However, current methods for removing oil from water are very inefficient and they're not environmentally safe at all. So all of my research in this project stems back from 2019 when I first was inspired to solve the microplastic problem. In this prior project, I investigated natural coagulants to clump the microplastics and then filter them out. And this was an inexpensive and non-toxic solution, and it used naturally abundant resources, but it was not as effective as it was expected to be. So in 2020, I investigated an electrolytic cell and an electromagnetic filter, but the electrolytic cell was very ineffective, so I did not want to further implement that. But there was a lot of evidence that demonstrated that the electromagnetic filter was effective for removing microplastics from water. So I wanted to further develop this, and I was led to my current research, an electromagnetic filter enhanced by the addition of metal oxides. So the way this method works is that metal oxides would be added to contaminated samples, and this will agglomerate the microplastics presented. These samples would then be passed through the electromagnetic filter, and the agglomerated microplastics that are clumped with the metal oxides would be highly attracted to the electromagnetic filter, thus allowing the majority of microplastics to be removed. I tested 3 different metal oxides in this project, and they were iron oxide, manganese dioxide, and nickel oxide. So in order to measure the effectiveness of these 3 metal oxides with the electromagnetic filter, I conducted both a spectroscopic analysis and a microscopic analysis. And through these analyses, it was proven that iron oxide was the most efficient to be using out of the 3 metal oxides that I used. In order to further optimize the efficiency of the iron oxide, I then consequently synthesized iron oxide nanoparticles because the nanoparticles have an increased surface area, which will thus allow an increased removal of microplastics. So in these 2 photos, you can see the electromagnetic filter that I used for this methodology. It's a simple design, but it was effectively able to replicate what it would be like. And so through this electromagnetic filter, contaminated samples would be passed through, and the microplastics would be highly attracted to the filter with the metal oxides, and then the contaminated water that is then cleaned will be collected in the beaker. So on the left, you can see all of the microplastic contaminated samples without the metal oxides added in, and on the right, you can see the metal oxides added in. And so those samples on the right would then be passed through the electromagnetic filter, and they would be successfully cleaned by using the filter. So I performed a spectroscope analysis in which I actually created my own homemade spectrometer. And this spectrometer measured the intensity of transmitted light through samples. And so across all of these tests, across different forms of microplastics, it was shown that iron oxide with the electromagnetic filter was the most effective methodology to be using, but manganese dioxide and nickel oxide did further increase the efficiency of the plain electromagnetic filter, just iron oxide was able to increase it the most. And this was again proven in the microscopic analysis, where the electromagnetic filter with iron oxide removed the most amount of microplastics in contaminated samples. But I realized that the electromagnetic filter wouldn't really be easily implementable, especially on mass scales. But it was proven that the iron oxide nanoparticles were highly efficient. So I wanted to further develop this, and then the ferrosponge idea was born. So this original ferrosponge concept was to just apply iron oxide nanoparticles to a plain sponge because a sponge would be very versatile and flexible, and it would be allowing it to be implemented in loads of different scenarios because of that flexibility. The iron oxide nanoparticles were also expected to have oil removal capabilities because through some more research that I conducted, I was able to see that they actually had oil sorbent properties. In order to further increase the efficiency of this plain ferrosponge, which only had iron oxide nanoparticles, I wanted to test other additives as well. The first additive I tested was bentonite, which is a clay compound that has known oil removal capabilities and is frequently used in oil drilling processes. The second one that I wanted to test was sorbent pads, which were expected to absorb oil. And the third was mineral spirits, which were expected to increase iron oxide nanoparticle retention, so it's an adhesion promoter. However, even though it was expected that all three of these additives would increase the efficiency of the ferrosponge the most, only bentonite was able to successfully enhance the removal of microplastics in oil and water. In addition to the additives, I also wanted to test different sponge materials in order to see how the material would affect the efficiency of the sponge. Through these tests, it was shown that polyurethane was the most effective to be using, and polyurethane is also one of the most inexpensive materials, which is a huge benefit. Again, spectroscopic and microscopic analyses were performed to measure effectiveness across all of these different tests that I conducted. So the final ferrosponge model was created by coating a polyurethane sponge in a mixture that consisted of iron oxide nanoparticles and bentonite. In the photo on the left, you can see the polyurethane sponge being coated in the sludge mixture with the nanoparticles and bentonite. In the middle picture, you can see the ferrosponge treating a microplastic and oil contaminated sample successfully. And on the right, you can just see the plain final ferrosponge model just to see what it would look like in general. So again, as I said before, it was expected that the iron oxide nanoparticles with bentonite, sorbent pads, and mineral spirits, the three additives, would be the best design, but this ultimately was not true. This was most likely because the sorbent pads actually reduced the net surface area of the sponge because it added another face. And this probably limited how much of the microplastics were able to be removed since it limited the area available for that. The mineral spirits probably were not very effective since they have a hydrophobic nature. And since the ferrosponge is treating water, it has to interact properly with it. But the hydrophobic nature of the mineral spirits would repel that water and prevent that from happening. But as expected, bentonite was able to efficiently improve the effectiveness of the ferrosponge the most, since it has recognized oil sorbent properties. And this is demonstrated in the picture to the right, where it was able to successfully remove microplastics and oil in contaminated water. So in the spectroscopic analysis, I used a laboratory spectrometer which measured the absorbance of different contaminated samples. So the lower the absorbance, the lower the turbidity, thus indicating that there are less contaminants present. And so I tested each of the 5 sponge types across each of the 5 implementations of iron oxide and the additives. And it was shown that iron oxide and bentonite was the best for cleaning microplastic contaminated samples. So this went to the next stage of testing, where I tested the iron oxide and bentonite across all 5 sponges and cleaned microplastic and oil contaminated samples. And it was shown that sponge 1 was the most effective material of sponge to be using. So then I went to the third round of testing where I developed my final prototype, and the iron oxide and bentonite coated sponge, which was created by using a polyurethane sponge, which was the material of sponge 1. And this was used to treat both distilled and natural ocean water. And in both instances, it successfully removed most of the contaminants. So in the microscopic analysis again, it was shown that iron oxide and bentonite removed the most amount of microplastics. And in the second stage of testing, sponge 1, again, as it was proven in the spectroscopic analysis, was the most effective material of the sponge to be using for microplastic and oil contaminated samples. And then for the final prototype testing, it was again proven that the iron oxide and bentonite coated sponge was the most effective implementation, and it was able to successfully remove microplastics and continue to be a very effective implementation. So
2
currently the
minutes.
ferrous sponge design is more suitable for smaller scales, such as acting as a tap water filter, a washing machine filter, a shower head, and much more of these smaller implementations like household applications. But the ferrous sponge design can also be easily developed for larger scales, since the general concept is simply just coating a porous, absorbent material in iron oxide nanoparticles and bentonite. And this larger scale methodology can be used to line oil skimmers, oil spill cleanup nets, and can even be developed into a larger sponge that's able to treat mass bodies of water to protect the ecosystems there. Now, the ferrosponge is currently filed for a patent and it is currently pending approval. And I'm also in contact with some local custom filtration technology companies so that I can further develop the ferrosponge on mass scales and implement it in the real world. I'm also in contact with an ocean research camp so that I can perform more research on how the ferrosponge can be implemented on larger scales in mass bodies of water to protect the organisms and the environment that are there. So overall, from this project, I was able to conclude that the ferrosponge is an effective, inexpensive, environmentally friendly, and easily implementable method for removing both microplastics and oil from water. The research leading up to the ferrosponge was vital for its creation and heavily shaped how the ferrosponge was formed. And now with the ferrosponge, it is hoped that this model can be implemented on both small and large scales across the world to reduce the harmful effects of microplastics in oil and water. Thank you for listening, and if you have any questions, please feel free to ask.